Right, good afternoon on this Friday afternoon. I want to continue on the topic of last class, so a little bit more about the Monte Carlo simulations, and then finally go on to radiative transport and diffusion theory. That sounds like quite a mouthful. It actually is if you really dive deep into it, but we're not going to do that. We're going to stay a little bit superficial here. I just want you to know about these things because in the at least for my mathematics people, for the lectures to come, there will be references to this. So you have to know a little bit about what is next. So I'm not going to talk too much about the applications of it. I'm going to talk more about that. All right. So first, quickly, I want to recap a few things that we discussed last week. So again, a quick shout out. First question is, I asked last week as well. The important one. What are the inputs I need if I want to use any of the scattering theories that we discussed? What I need to know. Yeah, that's let me make it a little more specific in that case. Let's say I want to calculate the scattering cross section. For example, using mean theory, which has calculator online. For the calculator online, I have to fill in some properties. It's not that many. So wavelength. Wavelength. That's one.
Refractive index.
Refractive index. And size of particle. Yeah, that's it. And then the refractive index, that's actually two. That's the refractive index of the particle and the refractive index of the medium that it's in. But these things are enough. If I know these, I can calculate scattering efficiencies, scattering coefficients. In the case of this mean calculator, that will also calculate phase function for you. So that's really obvious. Can someone explain to me what is meant with dependent scattering? Was really dependent on what?
It says in my no, I have no idea what it means.
At least, unless you're able to read those. I always have the problem that a week later. So dependent scattering. I'll help you out. So if you would take a bunch of particles and calculate the scattering, let's say, coefficient from that. What you would expect is, if let's say the number of particles is really small, so point fraction x-axis is really small. You would expect that if you would double the number of particles, that you would double the amount of scattering. So you would intuitively kind of expect that if you just keep increasing the point fraction, then that the scattering coefficient here which just increase. It's true if the point fraction is really low, that's exactly what happens. If the point fraction of the particle increases, there is no longer a linear increase, but not a non-linear increase. So it will still grow, scattering coefficient with point fraction, but not linear. We'll get to the y in a moment. So in order to describe this process, there were two properties, two functions, properties described. These are S.3 and 4, the pair correlation function, and then structure factor. Yes.
What's in the y-axis?
Sorry, the scattering coefficient. This is mu.
Oh, it's mu. Yes.
Yeah.
Thank you.
That's why it's difficult to reach one note.
Yeah. Thank you.
My Greek is really. So, what were these pair correlations? What was this pair correlation function? What was this structure? They were related. That's number 5. So if you know that, you can put one. You want something new? Do you remember that that illustration with the room full of people? You said that if you went out and everybody got to pick just the road number and the seat number, you would all come back in. Then some of you might have picked the same seat. That would be really awkward. So that is not happening. Everybody is sitting on his own chair. On the same thing happens with particles in a suspension. They cannot occupy. They cannot occupy the same space. So if you increase the volume fraction, then automatically some kind of organization, some kind of ordering in the sample space. And that ordering that is described by the pair correlation. So the pair correlation function basically is just the histogram of the distances between particles. And if the volume fraction is really low, then the particles can be almost anywhere. There's only a very small chance that they might be near each other. So then basically all distances are possible. But if the volume fraction is really high, they can only at best function of overlap. So then certain distances between particles are more likely than others. That is the standard effect. Now this is important because every single one of these particles scatters a field. And each of these scattered fields has a certain phase. If you then put the detector somewhere far away, all these fields reach that detector with their own phases, and they give the interference pattern. If the interference pattern is totally random, then we really don't care. But if these particles have positions that are no longer random because there are too many, and the phases are no longer random, and then this interference pattern is no longer random, and then we have to take that into account. And that is what the structure is. So the pair correlation function is really just all about the sample, because you have samples organized. But it has an effect on the scattering property, and that is expressed by the structure. But it's all related, intimately related through a answer to question 5 to Fourier. It's not a direct Fourier transform. It really looks like it. Okay, finally the question, and I just put it on the slide, so I'm not write it down.
So,
Yeah.
what was the answer to question 5? I didn't.
Fourier transform. Where in the expressions of scattering coefficient is the structure that included? I have that on the slide here. I hope you can read it. So this is essentially the same graph that I tried to draw here. So on the vertical axis is the scattering coefficient, on the horizontal axis the volume fraction. In blue, you see a linear increase, what you would expect for dilute samples. It's actually not relative. What happens in reality is the red curve, the non-linear increase of scattering coefficient. So where do we include it? We included this structure factor that's the function here. It's included in this interval. There's the phase function here as well. So we multiply phase function with structure factor from the integration. Now, if the structure factor would be absent, what would the outcome of the integral be? 1. Yeah. Well, it's the phase function is normalized by definition. So if I would integrate, so if the structure factor is 1. Then this integral term is just 1 and it vanishes, and then basically this expression reduces at this point. So for a dilute sample, structure factor is 1. Okay. Questions about this part? Questions from me to you. Okay. So Joseph, we have a chat. That probably means We cannot hear you very well, no. Okay, we'll try it like this. I hope this is better. All right. So in summary, the optical properties as we discussed them, for a single particle, we had coefficient. We had efficiencies and cross sections. So the efficiencies is the ratio of the, let's say, absorbed power of the incident power for the absorption efficiency, scattered power over the incident power for the scattering efficiency, simple Q. That's a dimensionless number because it's a ratio of two powers. Then the cross section has units area, and the absorption cross section you can calculate by dividing absorbed power with density. For the scattering cross section. These two are related. If you know the geometrical cross section G, then you can calculate the scattering or the absorption cross section from the efficiency. Okay, then that was for single particles. For multiple particles, like we saw, it can become a little bit more complicated. The coefficient is then the property. The absorption coefficient or the scattering coefficient is then the property that describes these samples. The formal definition is density of cross section. So you take you sum all the cross sections in the sample and then divide by the volume that they're in. Both for the absorption coefficient and for the scattering coefficient. But we also saw that it matters, that it really matters how the sample is organized. If you have, in case of absorption, if the absorbing molecules were contained inside the particles, we found a different absorption coefficient compared to when the molecules were in solution. That's what we discussed in the first lecture. And now, the last time we discussed what happens with scattering. If there's organization in the sample, because the particles cannot take random positions anymore, you also see the effect. Okay, so we're we're still here on the block tissue level, so we're again going to try to describe optical properties of these kind of cells, of tissue cells. So there's one approach we could try to take is basically the same as the way we calculate the scattering coefficient. We could try to calculate from such a piece of tissue the scattered intensity or the intensity at the detector by summing up all the electric fields, then integrate that over an imaginary sphere to get the total scattered power, and then go through these along these lines to get a scattering coefficient. We could try to do the same thing analogously for the incident for the detected intensity. So take the field at the detector multiplied with its complex conjugate, and then have the intensity. But that is not going for it. We can the first step may be feasible. We can maybe find all the little electric field parts corresponding to all these little volumes in the larger volume and calculate what that would be at the detector. But the problem is that if light is multiply scattered by such a bulk tissue, then each volume, each field from each volume is itself illuminated by all the other volumes, and it gets really quickly out of hand. So basically, this is not. So we need another approach, and there's two approaches that are basically equivalent, as we will see later on. One is Monte Carlo modeling, and the other one is radiative transport. So for the Monte Carlo methods, the overall idea, the thought behind it is that that there's this kind of link between probability and your detected signal. So this example we gave that if you look at, for example, a cuvette with an absorbing substance, following Lambert-Pierce law. So let's say that you would do an experiment and you would measure an E over 0 of 1%. If you translate that into probabilities, that then you would think, okay, 1 out of every 100 photons that I send through such a cuvette will get through, and the other 99 will get absorbed. That will also give me this 1%. So there's this link, this conceptual link between probability and the actual outcome of signals. So we can turn that around as well. If we can somehow calculate these probabilities, then we can use that as our best guess for the outcome of an experiment. So that's the idea. And of course, yeah. Now this may seem a little bit like an ad hoc thing to do, but I think it's kind of nice if you really look carefully. Then you could say that that this whole, it's really a pity that you can't read my slide titles, because obviously I put a lot of effort in those. Move the whole thing, it goes away.
Maybe if you read the chat, if you open the chat and close it, then because they said something.
Ah, yes, better. No. Leave it. So giant theory, this quantum electrodynamics is this whole almost complete theory of interaction of light with matter. And the one rule from that theory is that if you want to calculate the probability of an event, any event, a photon hits detector or a photon gets absorbed, you have to consider all the possible ways that this event can happen, all the possible paths, as it's called, which that can happen. You have to sum all these individual contributions. That's the end. And so that means if you can translate that into our situation, what we want to do is to determine the probability of detection. So let's say we want to determine the probability that photons go from this fiber to this fiber. We would have to consider all possible photon paths that lead from the one fiber to the other one. So in this cartoon, you just see a few of them. Some go pretty directly to the other fiber, while others take a long detour. So we would have to really accurately calculate the probability. We would have to take all these photon paths into account. But luckily, it's not that bad, because we also saw in this quantum electrodynamics that if we try to do that, if you would try to take into account all paths, for example, here in the middle you see the paths from some light source at S to some detector that is in the water O, and the drawing shows all possible paths and the graph here shows basically their contribution of each of these paths to the final probability. I'm not going to repeat the whole argument, but the effect was that some paths really don't contribute that much. So the ones here on the side don't contribute that much. It's only the ones in the middle that really account to the eventual probability. And that's a good news, because it kind of tells you, okay, light travels in a straight line. There may be ways of light to not travel in a straight line and go really weird ways, but these probabilities really don't just contribute that much. So we can consider light as traveling through, let's say, very narrow beams through the tissue. So that means that we can think of it as just traveling. Then at some point it is scattered, it changes direction, and then it travels again over such a beam-like path to the next side, and then continues. The second one, of course, so we can think of it as straight lines. That's one good thing. The other thing is that we do not have to take into account all of them. We just have to pre-select the important ones, and then we can ignore the other ones. So how do we do this pre-selection? So we're not just going to draw the ones that we think are most likely. We can do that by sampling the corresponding probability density functions, and more on that later. So instead of drawing all the paths, so for each path, the procedure means, again, this is directly copied, but much simpler from this electrodynamics. For each path, that means that we break it up in a chain of sub-events. So sub-events being here a propagation, then a scattering, then another propagation until it is detected. We calculate the probabilities of these sub-events. We multiply these probabilities to get the event probability of this event, of this particular path. And then we would have to, or as it turns out not to, we have to add all the phantom path probabilities for all the individual paths, for all the important paths, to find the total signal. So that's the basis of the Monte Carlo simulation. So very specifically, in this case, that would mean for such a path that the total probability of the path contains step lengths. So we need to know the probability of that certain step length. We need to know the probability that at the end of such a step, the photon is scattered. If it is scattered, we have to calculate the probability of it being scattered from one direction as one into another direction as two. And after that, it takes another step again. So we would have to calculate that probability again, etc., etc., etc. So these quantities, basically, it is just a chain of these events. The quantity step length, scattering probability, and scattering from one direction into another direction. They are treated here as random variables because every individual path is just a random path through the sample. Random variables, but they follow probability density functions that we know. And that's how we're going to construct the path. We're going to sample step lengths, scattering probabilities, directions from the probability distributions, and in that way we automatically get the important paths that we can use. So this is then how the Monte Carlo flowchart for such a Monte Carlo program would look like. So launching photon just means that you start simulation, you start tracking it, calculate the step size, calculate scattering angles, along the way check if it's absorbed or not, and then do some bookkeeping in order to make sure that we know what the position is, check if it is reflected, for example, or otherwise, or transmitted. And if it's not, then that loop continues. We take the next step, etc., etc. Until, for example, it is reflected. Then we store the photon data, whatever we want to use later, and start anew. So it is just a few simple steps that we have to keep repeating and repeating and repeating. So how do we sample these probability density functions? Well, there were two methods. One was very simple, but not very efficient. That was the so-called acceptance-rejectance method. So let's say we have some probability density function drawn over there. And we have a computer that gives us uniformly distributed random numbers between 0 and 1. So what we want to do is convert these uniform numbers between 0 and 1 to random variables that exactly follow this distribution. Now for the acceptance, for this particular method, draw a random number first that represents a point on the x-axis, somewhere over here. Then in the second step, you draw a new one, a fresh one, to represent the point on the vertical axis, on the y-axis. And then there's two options. Either that point falls below the curve or it falls above the curve. Now, so we go to compare if that second random, if it falls below the curve, so if I, the random value of I is less than the value of the probability density function, then we accept the random value for x, so the x coordinate. And if not, we throw it away and we start again. So that way we're only going to, so that way we make a selection of X values. And if we do that, if we keep doing that, we get a sequence of, let's say, accepted random values of X. And if you would calculate an histogram of these values of X, we would get exactly, we would see exactly that it follows the probability density function that we were. So in case of this PDF that seems well doable. Of course, it is. You can think of two scenarios in which this is not so efficient. What do you think? Well, when would this not be very efficient? Or not even possible? Yeah. So in what case would you? When would that be the case?
It's a probability person.
Yeah, then it's even more complicated. But let's ignore that possibility. No, so so as you can see is that we're only accepting the values that fall below the curve. So let's say that we have a curve that is high in the beginning of the horizontal axis, but then falls very rapidly to a low value. That would mean that in this region we would reject a lot of numbers because only a few of them would fall under the curve. So we would have to repeat this process a very, very, very long time in order to get a sufficient amount of points in this region to get a good idea of the histogram. So it can take a long time. It really take a long time. And the other reason, the other instance where it can take a long time is that we have to generate values between 0 and, well, not here it says 1, but between the maximum value on the horizontal axis. But if that maximum is infinity, then too it can take then it's not even possible to do it. So this works, but not always. That's the point. Enter the second possibility, which is a little bit more complicated to explain, but once you get the hang of it, it's quite elegant. So let's say that we have now an expression for that probability density function, not a graph, but just a formula. We can then calculate so-called cumulative distribution function, which is the integral of this probability density function. So in order to calculate it at some value x, you integrate from the minimum of x up to x. So let me make that graphical. So if we have an so this is the probability density function, something like this, p of x. So this is the small p. Then this integral from the minimum value on the x-axis to some value over there. Let's say this is the some value. This integral then calculates the area under this curve. So for each value of x, it calculates the area up until that value of x. So this will always be an increasing function. So what's the maximum of this function? Where does it stop? So this is the PDF, probability density function, and this is the what's the maximum value that the PDF can take? Yeah. 1, because the probability density function is by definition normalized. So if you integrate up until the maximum, you calculate the area, and that's under it's 1. And that simply means the probability of anything on this range happening should be 1. So if you calculate the area under the whole thing, it should be. Okay. So now in this case we calculated by integrating up until some value x. And we equate that to a uniform random number between 0 and 1. So we draw them from the computer, equate that to what we just calculated, and then invert this equation. So we try to solve for x. So we try to solve a random value of x by taking the inverse function as a function of that. In that process, again, will give us a sequence. If we repeat it, will give us a sequence of random x values. And if we then calculate the histogram again, we will get the original probability density function. All right. So with that, let's take a look at this propagation, or at this schedule again. And the first thing we want to do is calculate a step size, a random step size. So we have a number between 0 and 1 from the computer. We want to convert that to a random step size. In order to do that, we need to know the probability distribution of step sizes. Because if we have that, we can do this trick with the cumulative distribution function and invert it. So let's derive that first. Suppose that we have a probability, probability of absorption per unit length along a photon path. It can be a path to that, but it could also be a path inside the medium. Then, if we take PL and multiply it with an infinitely small length dl, then we would get a probability of absorption happening in this small interval. So PA is the probability of absorption per unit length multiplied with that interval. So it's a pure probability. Of course, it's normalized. If it's a pure true probability density function, then it should be normalized. Any integration boundaries need to be all possible values that L can take. So, but it ranges from 0 to infinity. Let's put that into step size. So no step size. Okay, but let's assume that PA is a constant. So along this medium. So this just constant makes it a little bit easier. So PA times DL was the probability of absorption in an interval dl. What is then 1 minus PA times dl? Let's get to the Yeah, that's it. That's that simple. Because it either absorbs or doesn't in this case. So 1 minus PA is the probability of not absorbing. Okay, what is then if I take 2 of these intervals back to back? What is then this product? It doesn't get absorbed twice. Yeah, that's well. Absorbing twice is not very likely, but let's say it does not get absorbed. It does not get absorbed over the larger interval.
Yeah, that's what I meant.
Yeah, I know. Yeah, so not the probability of not absorbing in this interval now of size 2 to DL. You have to be really precise. You can only do this multiplication if these 2 intervals are independent, in the sense that that the probability of absorption here should not depend on whatever happens here. But that's we'll assume that's right. Okay. So now let's take this whole photon path, the long path, and break it up in these in all of these little segments dl. So what is then the probability of not absorbing in the length of now, let's say from 0 to n times dl? The probability of not absorbing in a segment was 1 minus PA dl. Yes, to the power of n. Because they're all stacked and all multiplied. Okay. Now let's do some manipulation on this result. Take the natural logarithm on both sides. So on the left-hand side we have LNP. On the right-hand side we can move the exponent n in front of the natural logarithm. Write it like this. Now we can take dl as small as we like. So we can make the product dl really small, and then approximate ln 1 minus x as minus x. That works if x is small. So just by picking dl as small as we like, we can make this approximation. So ln p on the left hand side is n times minus p. Now exponentialize again. So now on the left hand side we have p back, and on the right hand side we have exponent minus PA times NDL, and NDL was just the length of the whole path, chopped it up in these segments. So we get exponent minus PA times L. So this is the probability of not absorbing over the whole path. Now this form of expression should look awfully familiar. It is just Lambert-Beer's law again. So this PA that we have here, we can identify that with the absorption coefficient, just as in Lambert-Beer law. So that means that the absorption coefficient is actually the probability of absorption per unit length. All right. So let's then continue with Lambert-Beer's law. So the likelihood of transmission, or likelihood of not absorbing, is then wow. What did I say? It's time for a break. Yeah, why not? Let's take 10 minutes and then continue. It's karma. All right, this is where we left off with Lambert-Beer's law, and we rediscovered Lambert-Beer's law by starting with the probability of absorption per unit length, and that turned out to be just the absorption coefficient. So the likelihood of transmission, or the likelihood of not absorbing, is then given by proportional to exponential minus PA times L. That means that the probability of not transmission, meaning absorption, in the cuvette is 1 minus exponential mu A times L. And this is then the cumulative distribution function describing the probability of absorption over a distance L or less. Red has length L. With the probability of not transmission, that means that somewhere in the cuvette, somewhere along the length L, the photon is absorbed. This cumulative distribution function is related to the probability density function, PDF, by this integral relation. So PL integrated from 0 to some value L would be the cumulative distribution function. Like that. So that means that we can use this result here, 1 minus and then differentiate in order to get the probability density function of absorption per unit path length. If you differentiate that expression, the result is this. So the likelihood of absorption per unit length is given by mu(a) times exponential minus mu(a) times L. You can verify that if you integrate this, and it's actually properly normalized if you integrate this from 0 to infinity, then the result is 1. So mu(a) times dl is the probability of absorption in an interval dl. P of L, mu(a) times exponential minus mu(a) times L is the probability density function of a free path length until an absorption event happens. So the L here is then the length the photon travels until it's absorbed. PLDL, of course, is then the probability of finding a free path length until absorption in some interval between L and DL. That is a convoluted expression. Still, and the cumulative distribution function 1 minus exponential is then the probability of absorption. So already. Okay, one last question. So, one additional question: if in blue we have the probability density function for path length until absorption, do you know how we can calculate the expected value of that path length, the mean value of the path length? Do you know how that is done? So PL is the probability density function, and I want to have the mean value, the average value, the expectation value of L. Now to this.
Oh, sorry.
Yeah, go ahead.
Then you have to do the integral by chance because then you take like
So you have to integrate. So you take L. You take L, you multiply it with P of L, so the likelihood of L happening, and then you integrate that from 0 to infinity. So for any probability density function, let's say we would have some for P of X, and then X times P of X integrated over the domain would be the expectation value, the mean value. But you can do that. You can multiply the expression there. So mu(a) times L times exponential minus mu(L), and then perform the integral. It seems simple. It's a little bit tricky because you need to use partial integration. But if you would like to do that, you can try that. I'll just give you the result here. Yeah, there we go. It's 1 over mu(a). The result is very simple. The expectation, the expected value of the mean free path length is 1 over mu(a). Makes sense. Mu(a) was in units of inverse meters, so 1 over mu(a) is the meter. Just then do the length. The mean, the expectation value, the mean free path length until an absorption. The interpretation for scattering is identical. We've gone through this for absorption, but you can do exactly the same thing, but then for scattering, you will get the same result. So mu(s) times dl is then the probability of scattering in an interval dl. You can do the same trick, but chopping up the path length in the segments of dl, and you will get this exact exponential form of the PDF. Also, 1 over mu(s) would then be the mean free path length until a scattering event occurs. And once you read it, you can do it. Use this to sneak in a new coefficient, the attenuation coefficient, the sum of the absorption and the scattering coefficients. Would then be the probability of so ut times dl would then be the probability of either absorption or scattering happening in this. 1 over mu t would be the mean free path length until either an absorption or a scattering event occurs. Okay. So we can now continue to finally continue to derive the expression for the photon step size, because we now know that the probability of a step size before the probability distribution before the density function, sorry, before either an absorption or a scattering event occurs is given by this exponential form with mu t there. So from that we can integrate and derive the cumulative distribution function. So we take the expression there and we integrate it from 0 to some value L to avoid all kinds of L side. There's a capital there, so you can we can integrate that and find the result is there 1 minus exponential mu t times L. Then following the recipe, we equate that to a random number. So ignore this part. We equate that to a random number, and then we invert, we solve for L. So that means moving one to the other side, take the natural logarithm, divide by t. And then here we have the expression that based on a random number between 0 and 1 gives us a random value for the path length. If we repeat that, if we draw a lot of random numbers and we calculate a lot of L's, we get a series of path lengths, and if we make an histogram of that, we will find that it exactly follows that exponential distribution that we still have. So this is then the step size. Well, the angles we already discussed a little bit. I guess you've already been looking into that in the assignment as well. That's based on the phase function. The phase function is the joint probability density function for scattering into angles theta and phi. But the joint is not so useful. We need to sample both angles separately. So we will join 2 random numbers, 1 for theta, 1 for phi. So we need to manipulate this phase function first to get individual PDFs for theta and for phi. In other words, we need to find the so-called marginal distributions from the joint of the distribution. That is done by basically by integrating over the other variable. So to find p of theta, we take the phase function and integrate over phi. We add all the possible values of phi to obtain the probabilities of theta only. For phi, we do the same thing, and we have to integrate over theta. Because it is in spherical coordinates, we actually have to integrate over sine theta. Now, in practice, for all the phase functions that we will encounter, there is no phi. There is no phi dependency in the phase function, so it's always just a function, only a function of theta. So that means that we can take a little shortcut. It means that the probability density function of phi will be constant, 1 over 2 pi. So that so just as a side note that there is no dependency on phi. That does not mean that it does not occur. It is just a constant, 1 over 2 pi. And for theta, that means that the integral from 0 to 2 pi over d phi will just add a constant 2 pi in front of the first function. Yeah.
Maybe we should pick, but why is it 1 over 2 pi?
Because it is uniform. It is constant. The domain for phi is from 0 to 2 pi. So if you want to have a uniform constant probability of phi, then it has to be 1 over 2 pi. Something? So the probability for each phi is the same.
Yeah.
So if you would integrate, and so we would have a PDF. The PDF for phi would be a constant.
Yeah, that I get.
Okay, that's it. Okay, and then because it's the PDF, it's normalized. So that means that by definition, from 1 to 2 pi of P of 5,
Yes.
it's normalized. So if this is constant, this integral normalized would be C1 is 1. So C1 is 1 over 5.
Okay, yeah.
From the normalization. Okay, and then the recipe for theta is then as follows. You can make it a little bit easier because we're not going to calculate random values for theta. We're going to calculate random values for cosine theta. So let's make a substitution. X is cosine theta, and rewrite the phase function as as a function of this x. So for the Rayleigh phase function, that means we had p of theta. P theta phi was 3 over 16 pi times 1 minus cosine squared theta. Multiplied by 2 pi, we're going to do that already. So p of theta is 3/8 1 plus cosine squared theta. So that means that p of x, where x is cosine theta, is now if we make the substitution, x is cosine theta, and we have to perform this integration from 0 to, so in step 2, we have to perform the integration from 0 to some theta, sine theta d theta. That means we have to, that means we can, if we want to do that based on cosine x, we have to change that integral as well. So sine theta d theta equals minus the cosine theta. Is minus dx. So instead of integrating this with the cosine squared over sine theta d theta, we can integrate this much simpler one just over x. And of course, we also have to then change the integration boundaries. And so if theta is 0, then cosine theta is 1. If theta is pi, then cosine theta is -1. So an integral from 0 to pi of something sine theta d theta would then run from 1 to -1 of d minus x. Bring the minus in front and cancel it by swapping the integration boundaries. So this simply becomes an integral from -1 to 1 over dx. Basically, made handling of the cosines and the integration then a lot simpler. But then once we have that, we can equate that to a random number and invert so that we get the random value of x, the random value of cosine theta. And then the last step, if we want to know actually the random value of theta, not of cosine theta, we can just simply take the invert the arc cosine. All right. So this is then the sequence of steps that we need to take to calculate scattering. One for phi, the simple one, and one for theta, which is a little bit more complicated. Okay. So we've done that. Then after a step and after we already calculated the new angles, we have to deal with absorption, whether or not the photon is absorbed. And this is tricky business. There are actually three common ways of doing it, and it's tricky business because simply because of the implementation in such a simulation, so not because absorption is per se tricky, but because of the implementation. One is called the micro Lambert-Beer law, and it works as follows: we start a photon with a weight of 1. And we reduce to after each step size. So let's say that the photon trajectory contains step sizes of L of S. After each step size, we reduce the weight by a variable factor according to Beer's law, so exponential mu factors. So the weight is
Why would you want to do that?
well, because if you have a tissue where absorption is present. Then if you would want to calculate the probability of photons going from, let's say, from here to escaping there, if you would not take into account absorption, you would get too many photons here. So
Why would you wait?
yeah, okay, maybe I should have started. Okay, let me. No, I'm not going to do this. I am going to start it. So what you could do is simply say, okay, I'm going to calculate the probability that it gets absorbed at some point, and if it's absorbed, it's gone, and then we must start up. Yeah, that is the most straightforward way of doing it. The drawback is that you may be doing a lot of work for nothing. So let's say that you're tracing a photon through the tissue, and you have already taken 10,000 steps, and you're really close to the detector, and bam, it gets absorbed. So that means that all these calculations that you have done are really for nothing. And the idea of doing it with weights is that okay, you can say, okay, then I'm still so some of the photon has still then still has chance to get detected, and I'm just going to count the weight at. But I did not do this whole trajectory for nothing. It just gets a little bit less weight when it reaches the detector.
Okay.
So it's pure for efficiency, for an efficiency point of view. But this way of doing it is actually not so efficient, because calculating an exponent takes resources, takes time. So another way of doing that is basically the same thing. So start with a weight of 1, and now not drop a variable factor, but drop a fixed factor. The fixed factor is then equal to mu a over mu a plus mu s. Basically, it is. So remember that mu a times dl was the probability of absorption within a certain segment. Mu a plus mu s times dl is the probability of absorption or scattering within a certain segment. So the dl's drop out. So what you have here basically is the ratio of the probability of absorption over probability of something happening. So that is a fixed factor. The pros of this is that it's much faster than this micro-Beer law. That's how the Germans would call it. It comes from a microbrewery, I guess. But weights can still get very small. So then what is here, the last one, is actually the one that you suggested that we should do. And that means that after each step, we draw a random number, and if that random number falls below the absorption threshold, then we're terminating the photon and we're starting the system. There are pros. Well, the cons is that it's not very efficient. That's what I just explained. The pro is, of course, that when this happens and you kept track of the photon, it is very easy to store the location where the light was absorbed. So let's say you're interested in it. Let's say you're interested in the locations where the energy is deposited. Then this way of implementing it is then very efficient. Okay. The weights can get very small. That is also a drawback. But we'll come to that in a moment. All these three methods are statistically completely equivalent. It does not matter which of these three you use. In the end, you will get the same amount of photons at the detector,
either by adding the weights or by just counting the photons which are not absorbed. So it is purely a matter of what kind of simulation do you want to do? Are you interested in finding where all the where the light is absorbed? And you would pick this one. If you're interested, if you need a fast simulation, you would probably pick the one. So that is, but it's completely different. So if it's not absorbed, or if only part of it is absorbed, then we can finally update the position. So what we'll do is we'll remember the coordinates. So we have the photon travels in the coordinate system X, Y, Z, and we keep track of its position after every step of seismics. In order to do that, we also keep track of the so-called directional cosines. These are so the photon travels in a certain direction in that Cartesian grid, and the cosines of the angles with respect to the axis in that grid are called the directional cosines. UX, so updating the position is, if you know this, is fairly simple. So the new X position is the old X position plus this directional cosine times the step size. Same thing for the Y coordinate. Same thing for the Z coordinate. That part is simple, just bookkeeping. This is a bit more complicated. Calculating the directional cosines after each step as a function of the angle theta, of the angle phi, and of the old values of the directional cosines. So this is deriving this is a very annoying exercise in geometry. So bookkeeping in geometry is basically what we need to do to track the photon position. Then the last step in the schedule, terminate the photon. Has it escaped? Then we count it as reflected, or we count it as transmitted. We store the things that we were interested in. For example, the escape angle or the path length that the photon took while getting there, the number of scattering events, etc. Whatever you want. But for the if we use the micro Beer law or the fractional drop, we're going to take one additional procedure, because as it said, as the drawbacks of these methods is that if you keep reducing the weight a little bit by a certain fraction, you started out with 1 and you reduce it at each step with a fraction, it can get infinitely small. And if somehow this photon does not cross a boundary, does not escape, but keeps propagating in the tissue, then at some point you're again wasting resources, because you're tracing a photon that really has almost no weight at all anymore. So at some point we should decide, okay, this is not going to work anymore. This photon will be dropped and we'll pick a new one. So that means that we're going to play Russian roulette with the photon. We define a certain threshold. So understand, draw a random number, a fresh random number. If it is less than 1/10, then we terminate the photon. And if it is more, then we continue with the photon, but we also increase its weight by a factor 10. And the reason for doing that is that in this step we might ditch, let's say 9 out of 10 photons. And in order to conserve energy, we increase the weight of the one photon that's replaced. So that photon with very small weight gets a new weight that's a little bit higher than the continuous photon. That's all there is to it. Yeah, so this is again the recipe. Okay. The whole trick. So why does this work? Why is it efficient? Is that by sampling these probability distributions, we select only the most likely paths. And that means that you don't have to sample all the parts, but you sample the most likely paths. Okay. As we said, we abandoned the rigorous approach of calculating electric fields. Monte Carlo is one way. The other way of treating this is very much related. It's called radiative transport shear. So let's discuss that. So one thing that it certainly has in common with the Monte Carlo approach is that that we can still regard the light as traveling across this beam-like paths. So really, the light can just be depicted as a collection of rays, beams that shoot out in the tissue. Okay, so we're going to describe in this transport theory. We're going to describe the transport of photon energy along these beam webs, along these rays. And I'm first going to introduce a couple of reintroduce a couple of quantities, so-called radiometric quantities that describe these processes. Many of them we already encountered. So the intensity, E, sometimes also called irradiance, is the photon energy per unit area per unit. When we're dealing with transport equation, like the transport theory, then the term intensity is usually reserved for light that is really incident on the tissue. So if you encounter the word intensity in this context, it actually means illumination. So we use it for to quantify the tissue illumination, and it depends only the intensity depends only on the geometry because it is light that is coming in. So not on the optical properties of the tissue, just of your only of your laser, your fiber, or whatnot. And then in the tissue, we have the radiance. So what goes on here is that we take a small volume inside the tissue. Light is shooting about along these rays. So that means that within that volume of tissue there is light incident along these beams paths, and we're going to evaluate the light that gets out along a certain direction. So that red line, that red beam, is the direction that we're evaluating, and we're evaluating the light that escapes, so that travels along this line in a small differential solid angle. So the radiance is then defined as the optical power that flows through a unit area, so power per unit area, into a unit solid angle, star rate, along the segment. So the unit is then watt per square meter per star rate. So that is the power flowing into a certain direction in this small angle. If you would add up all the power flowing, so integrate over the solid angle, then we get the fluence rate. So integrate over solid angles, so solid angle drops out. Then we have another quantity that has units watt per square meter. So it is the optical power flowing through a unit area inside the tissue in all areas, in all directions, in any kind of direction. So fluence rate is the integral of the radiance over speed. The fluence rate is the key property because it allows you to calculate how much light is present, how much optical energy is present at a certain location in the tissue. So if you would be able to calculate the local fluence rate in the tissue, you would multiply it with the absorption coefficient at that location. What you then calculate is the local absorbed power. So the absorption cross section has units of square meter. If you multiply it with the fluence rate watt per square meter, you get absorbed power plus. If you multiply the local fluence rate with the absorption coefficient, you get the local absorption power density, watt per cubic meter. The absorption coefficient has units per meter. The fluence rate has watt per square meter, so you end up with watt per cubic meter. This quantity, this is what you want to know. For example, if you want to use laser light for treatment, if you want to let's say do thermal therapy, if you want to burn laser welding, if you want to burn tissue, you need to know how much power is delivered at a certain point. So you need to calculate the fluence rate to get that. So other quantities that are derived from from the radiance are the so-called directional fluxes in a positive direction and in a negative direction. So let's the positive direction is then let's say it's defined over there. So that means that we take the radiance and integrate it over the forward hemispheres, let's say forward directions. And the same thing for the flux in the negative direction, the F minus that is integrated over the backward. Why would we do that? Well, if we take a small area again, small unit area in the tissue, and have these fluxes through that area in one direction and in the other direction, then the difference between the positive and the negative flux is the net flux. Netto flows through the area, and the total flux is the sum of that. If we go back to the geometry, so let's say we have a piece of tissue that is illuminated with some intensity E, then intensity E has units of watt per square meter. This directional fluxes also have units of watt per square meter. That means that right at the boundary, it's set to 0 here, the flux in the positive direction is equal to the incident intensity. That is all the light there is just before it enters the tissue. And also, if we calculate at the boundary, the light that is traveling in this direction, that is the light that is going to escape. So that will be the reflectance. If we define reflectance here in units of watt per square meter, that will be the reflectance. Quickly see what my next slide is. So I have a question. Let's consider this situation. If you have light here, have a tissue here which you illuminate with laser beam, for example. So there's an intensity over here, and at that boundary, we can calculate the fluxes. What is the total flux just beneath the boundary? F plus. Yeah, that is, so there is F plus. That is light going this way. The light has been on for quite a while, so we have been steadily launching photons into the tissue. What is the total flux just below the boundary? 0? No, it's not 0. No, because it certainly has. It's certainly equal to the light that you keep pumping it. So there is a flux in this direction. But this light scatters around here, and some of it goes back, some of it escapes. So there is also a flux in this direction. So that means that the total flux, the sum of these two, is basically the sum of the flux in the direction into the tissue, but also out of the tissue. It means that the total flux is higher than the incident flux, just below the surface. So just below the surface, you have light that the light that you send in, but you also have light that you already sent in before, and that is coming back. And that has some consequences, because that means, for example, let's say you want to suppose that this is a piece of tissue in the bladder. There is a malignancy there, tumor, I don't know, and you want to treat that with laser light. You want to cut away the tumor, but you also want to spare the tissue that is next to it. So what you need to do is to calculate very carefully how much optical power you would need to deliver to that site in order to damage the tumor, but spare the tissue. The only thing that you know in the experiment is how hard, how strong your laser is. You have a knob, you can turn it. What you can't control is the light that is shining, and it is also coming back. So you have to keep when you do that, you cannot just calculate what the laser intensity should be. You also have to take into account that there is still light in there. And if you shine more light on a tumor, that's okay. If you just destroy it. But also for the healthy tissue surrounding it, it can be a problem. So you have to take into account that the flux fluence rate is higher below the surface than is the intensity that you put in. Okay. So how do we calculate these? Fluences and fluxes and etc. Well, basically, we set up an LTI balance for a small piece of volume. So if we can calculate this as a balance of losses of light, gains of light traveling through that piece of volume. And you see it up there. So the change in power in time has two loss terms in red, and it has two gain terms in green. The loss terms are divergence of the light, so spreading of the light away from the volume. There can be light absorbed or scattered from the volume, that's the extinction. There can also be light scattered into the volume, that's the gain term, scattered. And there could be a light source inside the tissue. That sounds a little bit strange. I'm not going to put a laser in there, but you could set up this balance as well for fluorescent light, for example, and then the fluorescent molecule would be a light source. So the term has to be there. Okay. That on the top is the differential form that is manageable, and you can integrate that. You can set it up as a differential integral differential equation with differentiations and integrals in it, and you see actually you get the same terms. You get the same set of terms. So here you have the now in terms of the radiance, you have the change in radiance in time, which has loss terms over here, and there's gain terms. So a loss term due to divergence, a loss term due to UT, absorption and scattering, a gain term of light that is scattered into the volume, and a possible source term. Well, if the whole system is stationary, so the light is on and nothing really changes, then you get stationary response, and then the left-hand side of this equation becomes here. That could make it a little bit easier to solve, but still, it is almost not possible because you have 6 independent variables. If you have time, you have 7. You have the x, y, and z coordinates, but you also have the angles again with the axis of your coordinate system. So you have 7 independent variables. If you have time, also, and this equation is just you can solve it, but only for the simplest of geometries. So even though it's a beautiful result, it's not usable, not that usable. So we need a fix. The fix is quite old, a review of modern physics from 1943. Where it is shown that if you take this light traveling along these beams, taking random flights just as in Monte Carlo, that in the limit where the step sizes become very small, and in the limit where you have many step sizes in your trajectories, then you can describe this as a diffusion process, diffusion of optical energy. Which is good because the diffusion process or diffusion calculation is quick. You can derive it directly from the radiative transport equation. More on that a little bit later. There's also drawbacks. It is not very. It does not perform very well near light sources because then, basically the many scattering of the many events, the many steps have not occurred yet, so it's not so good close to sources. It is also not so good for tissues that have very high absorption, because if the absorption is really high, then the photons get absorbed before they had the chance to take many steps. So in these two circumstances, it does not perform well. But otherwise it is. Also, if it's a diffusion process, it implies that there is really no preferential direction that the light travels anymore. So it's really just no preferential direction. So the scattering kind of randomizes the direction that the light has. So if you would start with a laser beam shining light on it, then all the photons would have the same direction. But after many events, then the directions of the individual beam paths of the individual rays is completely randomized. So this diffusion equation is generally set up for the fluence rate, because that was the radiometric quantity of most interest. So we'll do that. So the fluence rate was the amount of power that flows through an area at some position into all directions. Power is, of course, the energy per unit time. So it is the amount of energy flowing through an area per unit time in all directions, joule per second per square meter. So for this diffusion, so we're going to set up this diffusion equation now. So we're going to describe or define a concentration of optical energy in the tissue. So the concentration would be joules, energy joules per cubic meter. That's the local concentration. It travels at the speed of light. It flows. This energy flows at the speed of light, which is equal to if there's a refractive index in the medium, it is reduced a little bit, so it is C0, the factor value, divided by the refractive index. It's the speed of light in the medium. So we can then write this relation between the fluence rate, joule per second per square meter, per square meter, and the optical and the concentration of optical energy. So the fluence rate is simply the speed of light times this concentration. So that means that the fluence rate is actually a measure of the concentration of photon energy. Now, if it's a diffusion process, that means that there is movement along a concentration gradient. So in this case, that means that we are going to describe it as light moving down the concentration gradient of optical energy. These processes are described by diffusion equation, by Fick's first law of diffusion. In general, this is the expression. So we have a net flux G down a concentration gradient, the C dx. So it's a gradient, a spatial gradient of spatial concentration gradient, and there's a proportionality constant x. So if we look at the units on both left and right hand side, we have watt per square meter on the left hand side for the flux. For the concentration gradient, we have the concentration was in joule per cubic meter. If we differentiate it with respect to the location, we get joule per meter to the fourth power, which means in order to have it match, that this proportionality constant has to have units of square meter per second to glue it all together. This is called the diffusivity in a general diffusion equation. But what we have to do now is we're going to write this general diffusion, this general version of Fick's law for photons. So we're going to write for this diffusivity the product of the speed of light again and d, diffusion coefficient, in meters. So once again, if you work out the units, then this work. Then this works out. And we'll fill it in now in the equation. So the net flux on the left-hand side is now the symbol F again. 4. D is the diffusion coefficient, and the gradient is that of the fluence rate. So it describes the movement of photon energy down the concentration gradient. The net flux as a function of the fluence rate, with the proportionality constant D, which is what the photon diffusion coefficient. Basically, this is the major result. But derivation of this was a little bit ad hoc. Okay, so we said, okay, it's going to be a diffusion process, so we're going to have to use Fick's law. And then if you do that, if you match the symbols a little bit, put in the speed of light in order to have it matched, then this is what that's. You can also derive it from this transport equation. I'm going to sketch to you how it works. because it gives a few interesting properties. So this is the beautiful equation that we cannot use on top. And what we're going to use is going to assume is a homogeneous infinite medium. So there are no boundaries. It's just all medium. Then of course you can have circle. If there's nothing else in there, you can have circle symmetry. And what we can do is express the radiance in the top equation as a expansion of spherical harmonics. That is just like the Taylor expansion, but then in a spherical geometry. So we expand the radiance as a function as an expansion of spherical harmonics. The phase function is also in there. P. It's a series of Legendre polynomials. So we get it's basically this whole expression gets expanded. It gets expanded. So the Legendre polynomials P Pn over there. So the phase function is a function of x, which is cosine theta. Becomes an expression like that. And the benefit of doing this is that we can characterize the phase function now in terms of its so-called Legendre moments. So you take the phase function, you multiply it with a Legendre polynomial, and you calculate the g. Would you do that? Well, because this is not what you have to calculate. Well, if n is 0, then the Legendre polynomial is 1. So that means that we're just normalizing the phase function, so the answer should be 1. So G0 is 1. G1 we also already encountered. That is the scattering anisotropy through definition. So basically we had these moments already, but what we can do now by this expansion is also calculate higher order moments that describe the phase function. And what then happens is that you can calculate the higher order moments, so G1, G2, etc., etc. And what turns out is that you get so-called similarity relations. The similarity relations are written here, so you have to take the product of the scattering coefficient with 1 minus G1. And if you find another pair of values, so mu s of mu, no, not again. Yeah, that is verbonden, right? Now I'm going to continue just a little bit because otherwise I'm not going to stop mid-sentence. That is let's do so. There is only about 10, 15 slides left, so we could also continue and leave them to. Yeah, is that? So the point here was that if you have a certain combination of US and G's and take US and multiply it with G1, if you can find two different values in US with a star and G with a star, where the product is the same, then the fluence rate, the radiance, etc., will be exactly the same. So that is the similarity. It is only so the results that you get, the radiance, the reflectance, whatever. It depends not on the individual values of US and G1. It depends on the combination. And if you expand this equation in more and more terms, then you get more and more of these similarity. It's all involving the US, the scattering coefficient, and the higher order Legendre polynomials. So a set of tissue with a set of optical properties, the US scattering coefficient and the phase function characterized by this, gives the same reflectance as a set of tissue with mu s star and G1 star, G2 star, etc. As long as these equalities hold. Now, because of this, because of this, the product µs with 1 minus T1 gets its own symbol because that's useful enough. It's µs prime, the reduced scattering coefficient. You guessed, of course, the whole thing in an approximation is that you can take this expansion and then ditch the higher order terms. So that's what we do. We take this transport equation, which could calculate all the spherical harmonics, but we're only going to take the 0th order and the 1st order. So only the terms involving G1, the anisotropy that we already have. So basically, then this whole thing is going to be described by µs prime. Of course, this truncation results in some loss of accuracy, some limits of validity. That basically we discussed them already before. It's not so valid near a light source. It's not so valid when absorption is really high. The remaining similarity relation is that from µs prime. So if you have a µs prime, µs times 1 minus g for one set of optic properties, if you define the µs and the G1 by the product of the is then the same, then you get the same result. Diffusion process of photon energy, fixed law of diffusion, so we can write the net flux as a diffusion coefficient times the gradient of the fluence rate. Potentially there's a source term in there, and then the diffusion equation is this. For the fluence rate, the diffusion equation for fluence rate is in contrast to the equation on the top, this one is solved. So here we can get expressions for the fluence rate. D, the diffusion coefficient, turns out to be, if you fill it in to the equations, then the diffusion coefficient is 1/3 times µs prime. So the diffusion coefficient that is just expressed as a function of the. Okay, so what is this reduced scattering coefficient? So if you look at the general generic photon path, then it can be, for example, many scattering steps, many small steps, and if the anisotropy is really high, G1 is really high, the average cosine of the scattering angle is close to 1. That means that the deviations that the photon takes along the path are pretty small. So it takes short steps, and after each step, it only marginally changes direction a little bit. So a photon like that would have a lot of difficulty of making turns. The mean free path between these scattering events was 1/µs. That would be right. But of course, the net result of such a trajectory is that the photon goes in at point 1, so to say, and has a certain direction at point 7. You could also achieve the same result if you're only interested in the outcome by taking much bigger steps over and using much larger angles. So that would give an equivalent result. So instead of having G1 that is close to 1, so many small deviations, we could set G. We could also have a situation where the diffusion, where the angles are isotropic, so no average preferential direction of direction of scattering, and would take larger steps to get the same equivalent result. The equivalent length, so you need larger steps in order to do that, and the equivalent mean path between the events is then going to be 1/µs prime instead of 1/µs, so 1/µs times 1 minus 2. The diffusion equation is solvable, as I said. And this is then the most important key result. The fluence rate inside an infinite homogeneous medium, so medium everywhere, as a function of time. So there's a light source in that medium that emits photons, and if you look then at the distance r away from that light source at the time t, then this describes the fluence rate. In green highlighted there is the product of c and t, so the time t and the speed of light c, so that is a length L. So you can also write that as You can substitute these occurrences of C and T with L. And there you recognize the exponent on the right hand side. You then recognize Lambert-Beer's law. So this is again an expression that the absorption takes place along the path of the photon. So the mu A is. That was time dependent. If we have a steady state solution, then the fluence rate does not change in time. Then the expression becomes even simpler, like this. So an exponential term that has an effective attenuation coefficient, as it's called, which is given by, it kind of gets out of hand with the coefficients here, is mu A divided by the diffusion coefficient, with this. If you work out, if you therefore the expression for the diffusion coefficient, it's the square root of 3 times mu A plus mu squared. Only a function of the optical. There's a little bit of controversy in the literature whether the diffusion coefficient should include absorption or not. So we have two definitions there. One is 3 times mu S plus mu A, and the other one is 1/3 times mu prime. The problem is a little bit that this controversy exists is that if you derive the expression using the transport equation, if you include diffusion, if you include absorption, you end up with this result, and if you exclude absorption with the idea that you can add it later using Beer's law, you end up with this result. So both appear valid. I think this is the right answer. Because it makes it more logical to unify the time result in steady state. So in books, in textbooks, you may encounter that definition of the diffusion coefficient. I'm using this. Final example. Because this was the fluence rate in an infinitely wide and infinitely deep medium, which is not very realistic. So let's take something that is a little bit more tissue-like. We have a block of tissue here, which is still infinitely wide and infinitely deep, and it is we have some kind of medium air, water on top of it. The light enters from the top in the plus z direction, and what we're interested in is, for example, the fluence rate in the tissue or the reflected light, the reflectance of the light that escapes. So what we would need to do then in this case is take this diffusion equation, set up boundary conditions to take this boundary into account, and account for possible mismatches between reflected images. The way to do that is to model that laser beam as a point source. So instead of illuminating with the laser beam, we're going to assume that all the light originates here. Then we can use that Green's function that we had in the previous slide. So all the light comes from here. It's then diffusing out. And in order to match the boundary conditions, we need to place a mirrored light source. It's not a real light source, virtual light source on top of the medium, because otherwise we would not be able to match the boundary conditions. So instead of a laser beam, we get two terms corresponding to both equivalent light sources. So I'm going to show you an expression now for based on this approach for actual geometry that is pencil beam, small laser beam that illuminates on the plus z-axis, which is going to be modeled as these two point sources. And what we've calculated is the reflectance as a function of radial coordinates. So if you're cylindrically symmetrical, so we're going to calculate that as a function of rho, which is the square root of x to the outside. Hou je vast? Dit is het. It looks complicated. But, if you look closer, or if you look between the square brackets are two terms separated by a plus. These correspond to these two light sources. They look more or less similar. Because they basically originate from the same kind of light source. There is distances R1 and R2 in there. these are expressed here as a function of depth in the medium z, and the rho that was the radial coordinate, and of a new position z0 and the diffusion coefficient. That position z0 is where this source, this equivalent source, is located, and we're going to place that at 1 over mu s prime. And there's going to be this mirror source as well. And to match the boundary conditions, we're going to place that at z0 plus 4 times the diffusion coefficient. It's really complicated. The point is this diffusion coefficient is then again expressed in terms of the scattering coefficient, the reduced scattering coefficient, I should say. The effective attenuation coefficient is expressed in terms of the absorption coefficient and the reduced scattering coefficient. So all the quantities that are in this equation, even though it's a complicated equation, all the quantities in there are determined by these two optical properties, UA and US prime. So that is sufficient to describe reflectance, even though the expression is a bit complicated. But of course, the computer you can really quickly evaluate expressions like this. It's much faster than Monte Carlo. These boundary conditions that we've been talking about, you can set up different boundary conditions for the same problem, and that gives a little bit of an issue, because if you use these different boundary conditions, which are equally valid for the geometry, but are a little bit different, then you get slightly different outcomes. So what you see here is the reflectance on the vertical axis as a function of the ratio of absorption and scattering. And as you can see, all these different boundary conditions give slightly different outcomes. So it is not. So it is still a little bit finger spitching a few of what the issue is. Then, of course, if you have that situation where the theory predicts different outcomes, then you would say, okay, the experiment is going to be a judge of which one is correct. So, of course, we tried that. We tried to do an experiment of reflectance as a function of different ratios of absorption and scattering, but it turns out that the experiments are not accurate enough in order to decisively say which set of boundary conditions is the right one. So it remains a little bit up to the person doing the calculations of the experiment which one to use. So a remark about the diffusion approximation. You can read. There's a whole chapter in the book which I recommend you do not read, because it is even more equations than I managed to put in the presentation. The problem. So it's simple. You can do fast calculations. The only thing is it is not valid in your boundaries. It is not valid in your light sources. It is not valid in the absorption coefficient. When this light diffuse, so we said the diffusion is the limit of many small steps. If you have a number of scattering events, the rule of thumb is that if the number of scattering events that the photon has experienced is larger than this ratio, so 4 over mu s prime, mu s times 1 minus t times the length, then you can consider the direction to be randomized. From a practical point of view, so let's look at it. So conclusion. Describing light transport in dual tissue, the radiative transport equation is exact. That's of course nice, but it's difficult to solve. 7 independent parameters, and you can only solve it in very simple conditions. The diffusion equation is much simpler. So you can get expressions like for reflectance, as I've shown you, for fluence rate. You can invert it, so you can measure reflectance and then try to extract the optical properties of the tissue. That's also good, of course, if you want to do diagnostic applications. But there is a limited range of fluidity, and that means especially close to the light source. So that means that if you would have an experiment where you have one fiber sending light in and another fiber picking light up, if these two would be too close together, then the diffusion equation, the diffusion approximation, does not work. Cool. So, some questions for you to think about. Not now, you can do it at home. Later on, this is what I wanted to share about the diffusion application. I wish you a very, very good weekend.
Same thing.
Yeah.